Hi everyone and welcome for this new episode of Data Science at Scale with VerticaPy. It's Badr speaking. In this video we will understand how to detect outliers. They are at the center of many use cases. Any business wants to know what is abnormal to take action. But first, let's try to have a clear definition. There is no perfect definition of what outliers are. However, a common definition is to consider any data point that differs significantly from the distribution as an outlier. As you can notice, outliers are subjective. The word significant can differ between different people. The potato in the picture is usually thrown in the trash by the supermarkets because it is not the regular caliber. This is a big waste for the planet. I found one in the heap of the supermarket and over ugly vegetables. One of the sellers was shocked that I took them. They are considered as outliers, whereas they are not. Did you know they represent 40% of what the nature gave us? Save the planet and eat ugly fruits and vegetables. Even if they are subjective, outliers might add bias to the distribution. They can be abnormal but possible values. For example, some rich people can have much higher revenues than the rest of the distribution. If we do a research on the average salary in a specific country, very high salary can distort the value. We will probably consider the median salary as more significant. Sometimes outliers are simply errors. They can be transmission error or typing and spelling errors. For example, if you let users entering specific information in your website without giving them predefined choices, they can enter a wrong birth date or an incomplete nationality. Example, if a user enters AU, what does it mean? Australia or Australia? But what if an outlier is not an error? The most well-known use case involving outliers detection are anomaly detections. Machine failure or system frauds are considered as outliers. It is important for any company to find any types of fraud in their business. Fraud detection is the priority of many organizations. Many frauds are happening every day and can lead to huge money loss. For example, credit card fraud is a very common use case. It can be card present fraud if a card was stolen or card not present fraud if not. This use case will be covered in another video. Many malicious activities are happening every day. And with the development of the web, we can see more and more web attacks. Cybersecurity is essential for any business. It can help identifying them to take fast actions. But anomaly detection is not only about fraud detection. Another use case is medical anomaly detection. Anomaly detection in the medical and public health domain typically work with patient records. The data can have anomalies due to several reasons such as abnormal patient condition or instrumentation errors. There are many business applications of outliers detection. But is it possible to represent outliers mathematically to catch them? There are three main outliers categories. Global outliers are the easiest one to catch and to understand. They are values which are far from the global distribution. For example, a student who normally withdraws no more than $100 suddenly withdraws more than $1,000 in the ATM machine. It is a global outlier and the behavior is very easy to detect. In our representation, the gray point is far from the distribution, so it is very easy to catch. On the other hand, contextual outliers are harder to find. Their values significantly deviate from the rest of the data point in the same context. For example, because of the very bad weather, people didn't decide to go out for the Black Friday, which decreased considerably the store staking. The store staking can be still good, but they will not reflect usual Black Friday behaviors. The gray point in the middle of the distribution is far from the line, but it is still in the middle of the distribution. The last outliers category gather collective outliers. The values as a collection deviate significantly from their entire dataset, but they are not global or contextual outliers. For example, some students decided to organize a party during COVID-19 quarantine, which led to an increase of cases in the region. As they are a group of people, they represent a part of a distribution, and they are then harder to detect. We can see the two main distributions and a smaller one in the middle. These 3 points represent a small cluster of collective outliers which are harder to detect. Bias can destroy the prediction. Let's take the example of a linear regression. The purpose is to find the hyperplane which will fit the most properly the distribution. Linear regression is quite good when the data are uniformly distributed. However, an outlier is enough to destroy the prediction. They add bias to the data, and models can tend to overestimate or underestimate a phenomena. They are not only affecting supervised learning models, but also preprocessing techniques like PCA or Z-score. PCA components can be biased, and Z-score techniques can become insignificant. Even more, let's draw the following distribution. We can identify two clusters. If we add an outlier, it can attract one of the clusters, making inconsistent ones. But then, how detecting outliers? There are multiple techniques to catch them. Supervised learning is one of them. We can train a model with patterns we already know. Let's take the following sequence: orange, orange, gray, orange, orange, gray, etc. It is then easy to predict when will come the gray points, which are representing the frauds. But frauds are changing and we cannot expect always the same pattern. We saw the pattern orange, orange, gray, so the next data point might be orange, but it is gray. The model can then easily do mistakes. Supervised techniques has many advantages. The number of techniques is very high and we have many ways to test them. They are most of the time easy to deploy and they allow a real data-driven experience. However, supervised learning can be used only when we have training data and tend to overfit when dealing with outliers detection. A use case can be churn detection in banks. It is not really common to see customers closing their bank account. The bank has access to customers' historical data and they can train models to learn the different patterns. The easiest way to detect outliers is to use rules and thresholds. If we consider the following distribution, we can build a rule based on a threshold. It can be Z-score, robust Z-score, or even an expert rule. Anything above or under the threshold is considered as an outlier. It will not identify outliers which are near to the global distribution. They are very easy to deploy and they have a very low complexity. However, they can only detect global outliers and they are most of the times underfitting. These techniques can work well in a banking system, where many fraudulent transactions are global outliers. The only techniques which can find all the different kinds of outliers are unsupervised learning. KMeans algorithm can easily help into catching outliers. It will create clusters based on an average process. Outliers will also attract a cluster. Clusters with few data points are considered as outliers. Unsupervised learning allows finding contextual and global outliers. But there are no ways of testing the model score, and sometimes unsupervised models can be very hard to deploy elsewhere. An ideal example could be anomaly detection on cranes. Each crane failure can lead to huge loss for any delivery company. Some other techniques like decomposition can also help detecting outliers. Robust PCA can identify what is abnormal in pictures. For example, I added a big mustache in my picture. Robust PCA can catch it and it will split our picture into two. Decomposition techniques have a low complexity and they can be used to find outliers on unstructured data. However, there are no way to test the accuracy of the model. An example can be to detect anomalies on some surveillance cameras. Different use cases have different requirements and different time constraints. We will see more deeply all of those into another video. But let's now see some best practices for preprocessing. Normalization can be used in all outliers detection use cases. It can even help detecting some of them. However, some data preprocessing and exploration techniques might not work. We must be careful when downsampling, imputing missing values or simply computing correlations. Downsampling might remove some outliers, making them impossible to be detected. Missing values imputation can add bias into the distribution and correlations might be totally distorted. Wow, we learned a lot. You now know what outliers are. It is time to go to some hands-on. It is very important to practice to get a deeper understanding. We will use VerticaPy and Jupyter to see how implementing an anomaly detection use case. We will see how. Creating a database connection. Generating a dataset. Finding the outliers using different techniques. Select the model we want to deploy. Deploying our model at the source of a data stream. Let's go! Let's use Jupyter Notebook to illustrate this topic. We can connect using database credentials. Be sure to have the same or an upper version to avoid compatibility issues. We load the SQL Magic extension. In VerticaPy, it is possible to work both in Python and SQL. All the computations are pushed to Vertica. Let's create the schema we will work with. We will name it Outliers Exercise. We will generate many different transactions, some regular between $0 and $100 during business hours, 8 a.m. to 8 p.m., and some during the entire day. We can add some high transactions during business hours. These transactions are between $3,000 and $20,000. And finally, some fraudulent transactions between $300 and $1,000, which only occur between 2 a.m. and 5 a.m. Let's see different techniques to catch them. We can represent the different categories using a scatter plot. It is not always possible. We are working in an easy two-dimension use case, but when the dimension becomes higher, it is hard to find features having obvious patterns. To see more clearly the separation between fraudulent and regular transactions, let's filter some of the transactions and let's consider only transactions that are lesser than $2,000. We can think that these data points are very easy to separate, but they are not, if we consider the entire distribution. This score will only catch high transactions and even not all of them. However, Robust score is more suitable for these use cases. It will catch both high and fraudulent transactions. Indeed, high transactions can increase too much the average. The median is much more robust and is more representative of the entire distribution. As the high transactions and the fraudulent are easily separable using a Robust score technique, the idea could be to create a Robust Normalizer, filter the regular transactions, and then use a KMeans with two clusters to represent the two other families. In VerticaPy, the models are created in database and they can be easily deployed. That's why we need to name them. We can fit the model. We can filter regular transactions which are easily detectable using Robust score, and create a pipeline model which will combine the min-max normalizer and the KMeans models. Pipelines allow to combine multiple models and thus simplifying training and deployment phases. We can verify if we code all the fraudulent transactions. We have 20 fraudulent transactions, and we code 20. All our work is happening inside the database. That's one of the big assets of VerticaPy. Everything is pushed to Vertica, so there is no unneeded data movement across the different systems. With VerticaPy, the code can easily be used to do near real-time computations. What about real-time? If we want to bring our model to the data source, it is also quite easy. We export our first Robust Normalizer model and our pipeline model. We can merge them using a very easy Python function. If a transaction has a Robust score lesser than 3, then it is a regular transaction, otherwise we proceed with the KMeans. Let's consider a transaction of $200 at 3 a.m. It is fraudulent according to our rules. Transaction at 2 p.m. of $50 seems to be totally regular. We can simulate the data stream and generate approximately 500 fraudulent transactions. We can see that we are easily catching them from the data source. We are doing real-time analytics. Do not forget that in that case we need really easy modeling and preprocessing, as we need fast computations to take action. With VerticaPy, we are using new generation objects which will simplify all the data science cycles. With few lines of code, we can solve any business use case. We can use the entire data set and we don't have to think on how moving the data out. It's a revolution. Thank you for watching this video. If you liked it, subscribe to the VerticaPy channel in LinkedIn. Visit our GitHub page and add a start to the project. Learn more by visiting our website at vertica.com/python. You can also subscribe to our YouTube channel. See you soon for another video.